Today, I shall discuss one important aspect of the second law of thermodynamics, Carnot heat engine, in lecture 12. And this engine is a hypothetical engine, not really existing, and nobody can materialize the construction of this type of engine, but one can assure that how much the maximum efficiency of a machine could be constructed. And a very brilliant engineer, Carnot, French engineer, at the age of 24 and the year of 1824, proposed this type of idealized hypothetical engine. And this engine consists of the 4 steps: to expansion and to compression, and comes to its initial state. As I have told earlier, that every engine must work in cycle. So this Carnot engine, let us take a very simple picture of this Carnot engine. Its pronunciation is Carnot, and this is the cylinder. This is cylinder, and the cylinder is insulated in every side, including the piston, except the bottom of this cylinder. Bottom of this cylinder is perfectly conducting, thermal conducting material. This bottom of this cylinder and other parts are insulated, so that heat cannot escape from this cylinder to this outside. And the heat engine, for conversion of heat into mechanical work, already I told one heat engine is required that works in a cycle, and here 2 reservoirs are there. One is H tier and other is L tier. It is high temperature reservoir having the temperature T, and this is the lower temperature reservoir. This is the temperature T dash. It is also called the heat source, and it is called the heat sink. And the engine will take off a heat Q from this H tier, and this engine does some work, minus W, minus sign here is given for this work done by the engine, and the rest of this heat is left to this sink unutilized, and this Q dash is rather called unavailable energy of the amount Q. This one is the unavailable. This energy could not be converted into mechanical work by this heat engine, so it is thrown to this sink. And naturally, Q minus Q dash, Q is taken by this engine, Q dash is rejected by this engine, and minus W, this is the amount of work done by the engine. And efficiency, I have already told, the efficiency is of this Carnot engine is efficiency of any engine, not that it is Carnot engine. Efficiency for any engine, it is the energy output and energy divided by energy input. Energy output is minus W and energy input is Q. Now let us see the inside. Let us go to the inside of our Carnot engine. And Carnot engine, actually the efficiency is related by this Carnot engine with this temperature of this source and temperature of this sink. And this Carnot engine, every step is reversible. Carnot, in case of a Carnot engine, every step is reversible to adiabatic steps to the two isothermal steps. And in this isothermal steps, the heat exchange is done from these reservoirs to this engine. And this cylinder consists of these 4 steps, and first step, n moles of this ideal gas have been taken. N moles of this ideal gas have been taken this as the working substance, or any fluid we can use as the working substance in this Carnot engine. So this n moles of this ideal gas we have chosen so that the formulation of this efficiency with this temperature in Carnot engine becomes easy, mathematically easy, and mathematical handling becomes not very difficult. So consisting of these 4 steps, and this step 1. Step 1 is a reversible isothermal expansion from volume V1 to volume V2 at a temperature T. This is the reservoir temperature is T. Means this cylinder or this engine, this cylinder or engine have been kept in contact with this hot engine, hot reservoir or HTR at this temperature T. So this reservoir is placed just below. This is the hot reservoir, hot HTR, temperature T, and its initial temperature is also P1, V1 and T. And in a case of isothermal process, how this heat is being flown from this HDR to this gas. As I have told, here this load P1, the external pressure, we can change only the external pressure, not this internal pressure of this gas. The external pressure P1 is exerted on this piston by keeping the weights, or better, keeping a handful of the sand grains over the piston to keep this load, so that the pressure of this gas is also equal to P1. So initial state of this gas is P1, V1 and T. And whenever if the sand grains are picked off from the surface of this piston, one after another, very small grains is picking up repeatedly from this surface, then P1 is decreased. Load is withdrawn from this piston. Whenever load is withdrawn, P1 becomes less, volume will increase, this gas expands very slowly, and which we call the process becomes reversible. When the expansion occurs, its temperature falls. Temperature also falls by dT amount. very small, infinitesimal small amount of temperature is decreased. To keep this temperature fixed, keep this temperature fixed, heat is flowed from this reservoir to this ideal gas or the working substance of this engine. So in this way, suppose this volume expands from V1 to V2. So if we, and pressure changing from P1 to P2 after picking up the sand grains over the piston. So the mathematics, reversible isothermal expansion from V1 to V2 at a constant temperature T, this first law, Q plus W1 equal to delta U. But delta U equal to n CVdT for n moles of this ideal gas, and temperature since constant, so dt equal to 0, so delta U equal to 0. So this one equal to 0, or Q equal to minus W1, go out right side, equal to nRT, temperature T, nRT ln V2 by V1. V2 is the final volume, V1 is the initial volume, and this is the equation number 1. So minus sign coming up, this system or the engine is doing this mechanical work according to IUPAC convention. And now this cylinder or this engine is detached from this HTR, and this engine is properly or say perfectly insulated by wrapping the every part of this engine by a good insulator. This one, this is this HTR. This cylinder is removed from this HTR, and it is also then insulated, or this piston or this cylinder have been kept over the insulated pad so that no heat can enter into the engine, or no heat can leave this engine from this engine to the surroundings. It means that the heat exchange between the engine and the surrounding is totally restricted and not possible. So this second step now, when it is kept under this pad, insulation pad, then again it is called second step, reversible adiabatic expansion from V2 to V3, V2 to V3, and this is done again by picking up the sand grains over the piston, and if we consider perfectly, then outside of this cylinder is kept in vacuum, so that no pressure is exerted except the weight of this sand grains. And now again picking up one grain at a time, and the load is decreasing, and so pressure falls from P2 to P3. Pressure falls from P2 to P3, volume rises from V2 to V3, as no heat is supplied to this engine. Naturally, the work the system does at the cost of its own internal energy, and the mathematics temperature, and the temperature falls. Temperature falls from T to T dash. T dash is the temperature of this LTR. So the expansion continues. Adiabatic expansion continues until the engine has got the pressure, has got the temperature T dash. T to T dash. T dash is the temperature of this lower temperature reservoir. So the mathematics is that heat given to this engine is 0, and what done in the second step, it is equal to delta U, or W2 equal to delta U means NCV, final temperature minus initial temperature. Or taking this taking this one, if we bring this T2 equal to minus NCV T minus T dash, equation number 2. This is the work done in the second step of this process, and second step is reversible adiabatic expansion. Now again, this engine, this insulation pad is removed. Insulation pad is removed from this lower bottom of this cylinder and kept in contact with this lower temperature reservoir, and it is again kept in this lower temperature reservoir whose temperature is T dash. Whose temperature is T dash. Now this third step, reversible isothermal compression, means a piston now coming back in order to reach this initial state. So this in this case the again sand grains are loaded over the piston to keep this P4, P3 to P4. P4 is high. P3 is increased to P4 by adding the sand grains over this piston. And so, whenever load is increasing, this piston is coming down. The piston is coming down to this portion. And heat, whenever compression occurs, the temperature will rise, and to keep this temperature fixed at a T dash, heat is removed from this engine to this LTR, and this heat is suppose Q dash. Q dash, the heat is removed from this engine to this LTR. To keep this temperature of this cylinder, working substance of this cylinder is fixed at a T dash. So in case of reversible isothermal compression, from V3 to V4 at a temperature T dash, Q dash, heat change from the engine to this lower temperature reservoir, plus W3, work done in this third step, equal to 0, as we have seen in case of isothermal process for this ideal gas, del U equal to 0. So this Q dash equal to minus W3 equal to A and R, and it is the T dash, and it is T dash and T dash ln natural log V4 final volume over V3 the initial volume, and equation number 3. This is the magnitude of this work done in third step. And now last step is the step 4. Again this one is removed. This one is removed. The engine is detached from this LTR and kept again in an isolated pad and insulation pad, so that no heat exchange occurs from the system to surrounding or surrounding to system. And now again these sand grains are being put over the piston, and load is increasing, pressure also increasing from P4 to P1. Sand grains are being added until the final pressure again becomes P1. So this P1, whenever the pressure is increased, it is coming to its initial portion, and in case of adiabatic reversible adiabatic compression for this ideal gas, there will be temperature rise, and temperature rise from T dash to T. Temperature rise from T dash to T. So temperature changing to T. It is the temperature of this heat source. So here, whenever the piston is coming to this position, means it is coming to this position A, and initial condition of this piston of this engine is being restored, as all engines must work in cycle. So this in this fourth step, the heat exchange is 0, and it is a W4 work done in the fourth step equal to delta U, or a W4 equal to delta U equal to A and CV, final temperature T and initial temperature T dash, and it is equation number 4. So this total amount of work done for this fourth step is W1, W2 plus W3 plus W4. You can see this W2 and W4, these two are equal in magnitude but opposite in sign, so W2 and W4 would be cancelled. So this net work, or the total work done by the engine, W equal to W1 plus W2, and putting here W1 minus this W1, here also W1 you can write minus nRT and ln V2 by V1, and in this case also this W3 equal to minus nR T dash ln V4 by V3. Or you can say, if you keep this minus sign here, minus W equal to ANRT ln V2 by V1, and this one would be the plus. But if we inverse this volume, V3 upside and V4 downside, then it will be minus RT dash ln V3 by V4. Let me see later. First of all, then again system is coming to this initial state. So if we draw this indicator diagram, then this possible work done by each step could be shown by means of this indicator diagram. First step W1. W1 is the A to B. This is the first step. Coordinates A is P1 and T, and coordinate B P2, V2 and T. T remains the same. Pressure volume is changing, but temperature remains the same. So temperature remains same, and Q amount of heat is taken by this engine from this HTR. So this W1 will be the car area of this car, area under this car AB. This one is the W1. Pressure times volume. And for this second step, W2 B2C, and it is the adiabatic, reversible adiabatic expansion. Volume is increasing. So this area under this car will give you the magnitude of this W. Then this two compression process, and then again this from C to it is coming D, C to D. It is the compression, and work done is W3, and the amount of heat rejected to this lower temperature reservoir is Q dash by the engine, and the work done on this engine is indicated by this area under this car CD. So this is the work done. This one is W3. And last step W4. W4 means again D2 it is coming. This A initial position, this one reversible adiabatic compression done to attain the initial state of this Carnot engine. And this area under this car will give you the magnitude of this W4. Last work done in the fourth step. So whenever the total work we shall consider this one, this area is done. This area will give you the amount of work done by this gas, by this engine in this expansion process, and this area will give you the work done on the engine. So this total work, net work will be the subtraction of this area A, B, C under this curve, the whole area minus the area under this curve C, D, A due to this compression. So this W becomes this area, enclosed area. This enclosed area will give you the work done by this engine, and it is the W. It is the W. And by measuring this area of this indicator diagram, it is also possible to get this magnitude of W. So we have illustrated all these processes made by this Carnot engine, and let us find out the efficiency. Let us find out the efficiency of this Carnot engine. So this minus W, work done by this engine, will be equal to minus W equal to nRT ln V2 by V1 and plus nRT dash ln V4 by V3. This is the one. Minus taken is inside, and these two becomes a plus. But V2 by V1 and V4 by V3 are not independent. If we consider the two adiabatic processes BC and AD, for this BC, which is a reversible adiabatic expansion, reversible adiabatic process for this ideal gas, the relation is T V to the power gamma minus 1 equal to constant. So in this case, at this position temperature T and volume V2, and gamma is the heat capacity ratio for this gas or the fluid used in the Carnot engine. So this one is T V2 gamma minus 1, and at this position it is T dashed. This T dashed, temperature getting down, and V3, here V3 to the power gamma minus 1. So this is the equation, say A. And this step A to D, again it is the reversible adiabatic process for this ideal gas. So in case of at A, the position temperature is T and volume is V1, and so T V1 to the power gamma minus 1, and at this position D, it is T dash and V4 to the power gamma minus 1, equation B. So A by B, this by this, T will be cancelled. So V2 by V1 to the power gamma minus 1 equal to V3 by V4 to the power gamma minus 1. As powers are same, so base will also be the same. So V2 by V1 equal to V3 by V4. This is the relationship between these four volumes. So instead of writing this one, we can also write nRT ln V2 by V1 and minus nRT dash ln V3 by V4. Getting this upside down, and since V3 by V4 equal to V2 by V1, so we can write nRT minus T dash and ln V2 by V1. So this is the amount of work done by this engine. Negative sign is indicating, this is the magnitude, and negative sign is indicating that the engine is doing this work. And we can also remember this Q. Q is also equal to nRT ln V2 by V1. In this first step, you can remember that I have written just now. So this efficiency is equal to minus W divided by Q. Energy output divided by energy input. So this by this, if we are doing this ratio, then ANR will cancel, ln V2 by V1 will also cancel, and it leaving this T minus T dash divided by T. Or we can write this 1 minus T dash by T. And this efficiency, the value of this efficiency will give you the maximum value. As you know, this sort of engine not possible to construct anyway. One thing is that the processes are not reversible, though the piston is frictionless, weightless and movable. How much mobile you can add to this piston, it is not possible to make a totally friction absent piston. And but also one thing is that in a process, in a cyclic process, consecutively isothermal and adiabatic, these two processes could not be done successively. This is also another drawback for making the construction. And the piston is also not possible to make it weightless, frictionless, movable. So in considering all these things, it is not a real engine. It is hypothetical engine, or you can say theoretical engine, or it will give the maximum amount of work of this engine working between these two temperatures, T and T dash. Of course, the automobile engineers can try to construct engine, and that engine they can compare how much efficiency of that engine is approaching to that of this Carnot engine. So Carnot engine, efficiency of this Carnot engine is taken a limit, and no engine is possible whose efficiency will be greater than predicted by the Carnot engine working between the same two temperatures. Now I shall start. From this already I have formulated the efficiency of this Carnot engine, and this W, I can also write modulus of this W. It is the, but it is to be remembered that it is the work done by this engine. This is the magnitude, and if we give sign, then it is the minus work done by this engine according to the IUPAC convention. So this eta, the efficiency equal to work done by this engine by Q heat supplied from this HTR, and this one equal to T minus T dash by T, or we can write 1 minus T dash by T. This is the expressions of this efficiency of the Carnot engine, which is a perfectly idealized engine, and maximum amount of efficiency you can get it from this expression. And several outcomes, very simply, several outcomes are available from this expression. And the first one, perpetual motion machine of first kind. Let us consider perpetual motion machine of the motion machine first kind. From this expression, we can conclude it is not possible to construct such type of machine. As you see, this W equal to Q into 1 minus T dash by T. But if a Q equal to 0, no heat is given to this engine, then automatically this work done by this engine is also equal to 0. Very easily you can show the perpetual motion machine of the first kind is not possible to construct. And the second one, and perpetual motion machine of the second kind. Let us consider this type of perpetual motion machine of the second kind is possible or not. From this expression, if we consider it is not this perpetual motion machine, is that if we construct an engine taking heat from a single source, taking energy from a single source, and whether it can do any mechanical work. And in one source means T equal to T dash. And whenever T equal to T dash, only one source is there, not these two reservoirs, only one reservoir. Then from this T dash and T equal to these two are equal, so 1 minus 1. So in this case also W equal to 0. No work is possible for any engine connected to a single reservoir and doing this work, doing the positive work to the surrounding. Positive work to the surrounding means we are getting that amount of work out of this engine for our own benefit to run the machine. And this third one say this efficiency is equal to 1 minus T dash by T. And efficiency, this states that the efficiency will be always less than 1. No engine will be 100% efficient. It is not possible for any engine to construct which is having the 100% efficient. So efficiency is less than 1. This one is fraction. And eta will also be fraction. Eta will be equal to 1 only when this T dash equal to 0 Kelvin and T equal to infinity Kelvin. In this case, the efficiency equal to 1 means the heat is completely converted into work under these two conditions. But we all know these two conditions are not possible to realize in practice. So efficiency will be always less than 1 or less than 100%. Then fourth comment. Unattainability of absolute zero temperature. Unattainability of absolute zero temperature. From this relation, we can say efficiency always less than 1 as stated by this Max Kelvin pK statement. pK statement shows that the efficiency must be always less than 1. So this efficiency must be less than 1 minus T dash by T. Always this efficiency must be less than 1. So by mathematical way, we can say this minus T dash by T is less than 0. Or you can say this T dash is always less than 0 absolute. 0 degree absolute. This T into 0 equal to 0 minus means always it will be greater than 0. Greater than 0. If we lift this minus, then this inequality sign also becomes reverse. Means the temperature of this sink must always be greater than 0 degree absolute. And so it is already concluded a very important aspect that we never reach the absolute 0 temperature. It is not possible. It remains unattainable. Different scientists have tried to reach this absolute 0 temperature, as I have seen in an article from this Colorado University. A group of scientists in Colorado University, they have tried to cool down one cesium crystal by means of adiabatic dimagnetization process. But still then, they reach this temperature, say 10 to the power minus 6 Kelvin, but still then, that means 0 and 501. Very small temperature, but still then they fail to reach a 0 Kelvin temperature. If it would be possible, then second law of thermodynamics is not applicable, not viable, or cancelled, totally fails. And the fifth one, sixth one, unattainability of absolute 0, fifth, and this is sixth. Unattainability of absolute 0, this is the fifth comment, this is the sixth comment. And in this case of the efficiency is equal to 1 minus T dash divided by T. So the efficiency can be increased by lowering the temperature of the sink or increasing the temperature of the source, or by both. If T dash is decreased, then efficiency will also be increased. If T is increased, then also efficiency will be increased. We may compare in which case the efficiency will be greater. Say eta 1, say we are reducing this efficiency of this sink, or by increasing we are decreasing the temperature of this sink, or by increasing the temperature of the source to the same extent. So this eta 1, suppose eta 1 is the efficiency, whenever occurs, the sink temperature is decreased. So by differentiating this one, this dN1, the eta 1 change in efficiency by doing by decreasing the temperature of this sink, keeping the temperature of the source fixed, then it will be minus dt dash divided by t. And the reverse. So whenever the t dash is kept constant and t is increased, then suppose the efficiency in change is d eta 2 or increased equal to this one equal to 0 and this one minus means plus t dash divided by t square into dt. But this decreasing the temperature of the sink and increasing the temperature of the source, they are at the same extent. So this dt minus dt dash equal to dt. Then d eta 1 by d eta 2 is equal to, keeping this ratio this 2, dt minus dt dash will be cancelled, and so it will be t by t dash. One t will be cancelled, this one is down, so t dash t by t dash, and since t is greater than t dash, so this is also greater than 1. What does it mean? The engine will be more efficient if we lower down the temperature of the sink rather than increasing the temperature of this source to the same extent. But it is our usual, and it could be seen in our experience. Any automobile engine will be much more efficient in winter season than in summer season, as this sink is always taken the atmosphere, and whenever the atmosphere temperature is lowered down in winter season, the efficiency of that engine automatically will be increased than in comparison to in the summer season, where the temperature of this atmosphere is high. But in every case, it is not possible to control this temperature of this environment, temperature of the sound. You cannot lower down the temperature of the surroundings. It is not possible. Rather, we can increase the temperature of this source. Suppose in a steam engine, we can use the high pressure steam. In ordinary steam, whenever water is boiled, then its temperature is 100 degrees centigrade or 373 Kelvin. But if the pressure over the piston in a boiler is increased, then water will boil at high temperature, and it is possible for in a high pressure boiler the temperature is equal to 550 Kelvin. It is possible to increase this temperature of this source of this steam by using the high pressure boiler. In that case, efficiency is of about 65%. 65%. And T dash is the atmosphere, and it is taken, suppose 40 degrees centigrade. It is also degree centigrade. By using the high pressure boiler, the temperature of this steam becomes 550 degrees centigrade, and temperature of the source, let us take this atmosphere, and it is 40 degrees centigrade, and whenever this one is done, whenever this one is put here, then efficiency found to be 62%, but practically the efficiency is not possible to attain this one. This one is the maximum value for this hypothetical Carnot engine, and it is about 40%, above the 40%. So the seventh one, this is seventh one. Now all of us, we are knowing that efficiency is always less than 1, and so this work available equal to Q into dt by T. So the efficiency of the work done by this engine is heat supplied into dt by T fraction. Means dt by T fractions of this heat supplied, we can get the amount of work done by this engine in Carnot engine, in Carnot cycle. And this is the seventh one. And this eight you can say, we can show the efficiency. Efficiency is a function of T and T dust. And efficiency does not depend on the amount of this working substance taken in this engine, as the efficiency is an intensive property. Efficiency is an intensive property. So efficiency does not depend on the amount of this material, of this fluid taken in this engine, one thing. And second one is that the efficiency does not depend on the nature of this working substance, whether it is ideal gas or van der Waals gas or steam or steaming in case of steaming it is steam, in case of petrol engine it is petrol, vapor and air mixture, in case of diesel engine, diesel vapor and air mixture. But in case of Carnot engine, the efficiency does not depend on the nature of this working substance. And not only that, and third one, the efficiency does not depend on the nature of this work done. It is not only applicable for this mechanical work, but it is applicable for any type of work done by this engine. So these are the all conclusions. These are the all conclusions, critical conclusions or critical discussions on this efficiency of this Carnot engine. And now I shall give one problem for doing at your own home, and see where I am giving now this problem consisting of 6 steps, and how much the expressions of this efficiency of that engine would be. One problem has been given here, which has been set in Baroda University in 1994. An ideal gas goes through a cycle consisting of alternate isothermal and adiabatic curves as shown in the following figure. And figure is a pressure volume diagram, and starting from A, isothermal at this temperature T1, and BC adiabatic, CD isothermal at the temperature T3, and DE again adiabatic expansion, and up to from this to this adiabatic expansion processes are there, and the compression isothermal at the temperature T3, and it is again adiabatic coming to this initial state A. You can take this here, this Q1 heat is taken by this engine, here Q2 amount of heat is taken by this engine, here Q3 amount of heat rejected by this engine. You can consider. And the isothermal processes proceed at temperature T1, T2 and T3. And this is T3. Find the efficiency of such a cycle. What will be the efficiency of this whole cycle? Considering all these steps, there will be 6 steps, 6 work done. You will have to calculate, then you will have to sum up and find the efficiency of such an engine if in each isothermal expansion the gas volume increases in the same proportion. That means in this expansion, isothermal expansion, this is isothermal expansion. That means VB by VA equal to VD by VC, and this has been given as a clue. This isothermal, in case of isothermal expansion, the volume increases in the same proportions. This one, and you can do by your home, and it will be 1 minus 2T3 divided by T1 plus T2. If you fail, you can consult. If you like, then Thermodynamics Principles and Applications by NC Day, a New Central Book Agency publication, page number 44. And this is all about this Carnot engine. And next class I will try to explain the refrigerator, which is the reverse of this Carnot engine. So thank you all who are watching this video. If you like, then please subscribe. Thanks again.